Okay, welcome back, students. Let's cover 4.2 today, vector spaces, introduction to vector spaces. Okay, share my screen. Okay, 4.2 is on vector spaces. Okay, and let's define what a vector space is with 10 axioms. Okay, definition. Let V be a non-empty set whose elements are called vectors. On which is defined an addition operation and a scalar operation with scalars in set S or F. Okay. We call V a vector space over F if the following 10 conditions are satisfied. Okay. A1 is closure, okay, under addition. Okay. For each pair of vectors, U and V, in V, the sum of U plus V is also in V. Okay, so we can't get something out of we can't add and get something that's not in V. Okay, if both U and V are contained, if the vectors are contained in this set, okay, this set of vectors, then when we add the vectors, we can't get something outside of it. Okay, so closure just means that you don't get anything when you do an operation. You don't get anything outside of what you originally started with. Okay, a counterexample of what is not closed would be the set of integers over division. Okay, if I divide two integers, I'm not guaranteed an integer when I divide. Okay, so that's not going to be an integer. Okay, because 4 does not divide evenly into 1. And so I would end up with a rational number instead of an integer. So integers over division is not closed. But what we want here is we want to say, well, make sure that that addition is closed. Okay, for these vectors. Okay, A2 is that closure under scalar multiplication okay, so if I multiply a scalar times a vector, okay, I should stay within the vector space. Okay, for each vector u in V and each scalar R and F, scalar multiple RU is also in V. Okay, so once again, we're not outside the set V. Okay, axiom 3 or condition 3. Okay, for all vectors U and V that are elements of the vector, the set V, the non-empty set V of vectors. Okay, U plus V is equal to V plus U. So a commutative property of addition. Okay. Okay, A4. Okay, for all UV W that are elements of V. Okay, U plus V plus W in parentheses. So we're adding V plus W first, and then adding that to U. That's the same as U plus V, and then we add on W second. Okay. Okay, and so some associative properties. Okay, and an additive property of associativity, or we can call it an associative property of addition. Okay. A5 in V, there is a zero vector denoted as zero vector, satisfying U plus the zero vector is equal to U. Okay, so an additive identity for all U in V. Okay, A6. For each vector, U, which is an element of V, there is a vector negative U. Oops. Negative U, which is an element of V, such that, oops, sorry, such that U plus negative U is equal to the zero vector. Okay, so an additive inverse identity Okay, additive inverse property. A7. For all U in V and 1 in F, 1 times U is equal to U. Okay, so a multiplicative identity. Okay, A8. For all U in V, okay, and RS in F, so RS are scalars, RS of U is equal to R times SU. Okay. Okay, A9. Okay, for all U and V that are elements of V, and R an element of F, R times U plus V is equal to R U plus RV. Okay. And then A10. Okay, for all U and an element of, for all U, which is an element of V, and RS, which are elements of F, R plus S times U, vector U, is equal to RU plus SU. Okay, now in the previous section, 4.1, we stated these as properties of vectors and vector addition in the normal sense that we say, hey, this is a vector. This is a vector that just has number elements. Okay, and we've defined vector addition in a certain way. We just add the components, okay, together, and then we've defined scalar multiplication in a certain way. We just distribute the scalar to each component in the vector and multiply. So we've defined those two operations, and that is a vector space. All 10 of these hold for that type of vector understanding. Okay, depending upon how restrictive we get on V, depends on if it's a vector space or not. If it's an element of, say, R, F is RS are elements of R, the real numbers, and U is R to some n degree, depending upon how many elements in the vector there are, then that's a vector space. Okay, that's kind of the least restrictive environment that we have. You can restrict V even more, and then kind of all bets are off whether or not that's a vector space. You'd have to test it. Okay, but there are other things that are vector spaces that don't hold to the normal ideas of what a vector is and what and how a vector would behave. Okay, so let's go through and explore 6 examples of vector spaces. Okay, these are vector spaces. They hold all 10 of these properties of these axioms. Okay, but addition and scalar multiplication may not be defined in the same way, depending upon the properties of the vector spaces that we're given. Okay, but there has to be some operation of addition and some operation of scalar multiplication that satisfies all of the axioms or all the properties. Okay, so examples of vector spaces. Okay, one. Okay, Rn. Okay, I just alluded to this as well. The real vector space of all ordered n tuples, I should say, n tuples of the real numbers. Okay, in which we could say that the vector x is equal to x1, x2, x3, dot, 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 to xn. Okay. Okay, number two. Okay, C, which is a script C. Okay, I'll try to make that a little bit better. It's hard to do the scripts, so it kind of looks like a crescent moon. Okay, so script C, and then to the nth power, okay, or the nth degree. Okay, and this is the complex the complex of vector space of all ordered n tuples of complex numbers. So we would just replace, say, x with y, and y has y1, y2, dot, 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 yn. But instead of real numbers, we're allowed imaginary numbers now. Okay, and complex numbers. Okay, number three. So that is a vector space as well. Okay. Now we get into our linear algebra. Okay. So M of m by n of all real elements. Okay. So if we have an m by n matrix, okay, and with real elements, then that is a vector space as well. That satisfies all 10 properties. Okay. This is the real vector space of all m by n matrices okay, with real elements. Now, if I change the dimension of the matrix, then it's outside of V. It doesn't work. Okay, you have to have, it's all the say 2x4s and with real elements, and then you're in a vector space. Okay, if you change the dimensions at all, then you're outside the vector space. You're no longer inside that consistent set. Okay, so you have to choose your M and N and then stick with it. Okay, likewise, we could let N and M be the same number. Then we just have a little bit different shorthand. M sub N Okay, this is a square matrix. So this is basically the same thing, but M and N are the same value. Okay, so this is the real vector space of all n by n square matrices with real elements. Okay, number 5. Okay, C, this is actually a C, okay, not a script C. Okay, and then K is in parentheses, that means derivative. That's the kth derivative, okay, of C, okay, of I. Okay, and so what is this? This is the vector space of all real valued functions that are continuous and have at least k continuous derivatives on an interval I in R. Okay, so this is just saying, look, you give me a function, and if I can find a second derivative of it, and I can get a set of all functions that have a second derivative. It doesn't matter if they have a third or fourth or fifth or whatever, as long as they're differentiable, then that would be C2I, and it has to be on a specific interval. Okay, you have to give me the bounds for that interval as well. Okay, that would be C and then 2 in parentheses. So that'd be all the second, all the functions that are able to be differentiated twice. Okay, which is a pretty big set. That's an infinite set. Okay, but it still has, even though it's an infinite set, it still has bounds. You can't go outside the bounds. Okay, there's an infinite number of items in it, but it still has boundaries. Okay, if it doesn't have a second derivative, then it's not part of the set at C. If it was C2, okay, then we could have C3, C4, C5. Okay, and those would be all the ones that have third derivatives and fourth derivatives and fifth derivatives. Okay, okay, because eventually you're going to get to 0, and you're going to end up stopping, especially if you have a polynomial. You may go on to infinity forever if you have something like a trigonometric function where you just keep oscillating back and forth, cycling. So it really just depends on the function. Okay. Some of them are going to peter out, and some of them are going to go on forever, and some of them, will have other behaviors. Okay, number 6. Okay, Pn of R, the real vector space of all real valued polynomials of degree less than or equal to n with real coefficients. So basically your run-of-the-mill polynomials, real coefficients. So Pn of R would take the form of some constant plus a coefficient times n or times x. Okay, plus a coefficient times x squared. It's a plus, sorry. Plus a third coefficient times x cubed plus dot 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 all the way to an nth coefficient times x to the n. Okay, and so we can add polynomials together. Okay, by combining their like terms, we can multiply polynomials through by a constant, which just means that I would distribute it to each term. So scalar multiplication and addition, they work similarly to vector addition and vector scalar multiplication. Okay, so really just interested in saying, okay, do these guys have the same behavior as normal vectors? Okay, if they have the same behavior and they stay within the same bounds, then they're called vector spaces. Okay, and this list is not exhaustive, by the way. Okay, there are as many vector spaces out there as you can think of. Okay, you can come up with some function and define addition as, and we'll see this later, as adding two integrals together, or taking multiplying by 3 and then adding 2 would be defined as some sort of vector addition, some strange sort of addition operation. Okay, and so again, these are just the ones that we kind of deal with on a daily basis in kind of the real world. But you can define your addition and your multiplication operations however you want. And as long as they fit those 10 axioms, then it's still defined as a vector space. Okay. Okay, so again, just that caveat that this is not an exhaustive list. This is just a list of things that we may have seen already. Okay, let's look at the vector space of the n by n matrix. Okay, and see, let's just take an example. Okay, show that M sub 2, okay, of R is a vector space. Okay, let's just show that this thing does, in fact, satisfy all 10 axioms. All 10, I should keep saying axioms. All 10 properties. I mean, you kind of think of them as they are axioms, but they're the conditions, all 10 conditions. Maybe I should say conditions from now on. Okay, all 10 conditions that satisfy the vector space, it being a vector space. Okay, is V a vector space? Okay, is M2R a vector space? Okay, so let's let A equal A1, A2, A3, A4. That's my first 2 by 2 vector. B equaling B1, B2, B3, B4. My second 2 by 2 vector, and my third 2 by 2 vector is C1, C2, C3, C4. Okay, okay, let's first check property 1. Okay, vector addition. Okay, do I retain a 2 by 2 vector if I add vectors together, these 2 by 2 vectors? And yes, I do. I would get A1, A2, A3, A4 plus B1, B2, B3, B4, and that equals A1 plus B1, A2 plus B2, A3 plus B3, and A4 plus B4. And that is an element of M2, so it's closed. It's closed under what we know as vector addition, okay? You kind of think of this as you know, each of those elements is a component. And so we're just adding components together, okay, depending upon where their position is. Okay, A2. Okay, we're adding elements together, I guess we call it. Okay, A2, R times A. Okay, where R is an element of the real number system. Okay. Okay, it's an element of F, which is in the real number system. So let's look at R times A1, A2, A3, A4, and again, we're just going to distribute R to each element here, and we get RA1, RA2, RA3, RA4, which is an element of M2. So check. So we'll check here. Check, check. So that's closed under scalar multiplication. Okay, A3. Okay, does A plus B equal B plus A? Well, A plus B, we saw that was this guy up here. Okay. So A plus B is equal to, okay, A1 plus B1, okay, A2 plus B2, A3 plus B3, A4 plus B4, okay, and that's equal to, and addition of real numbers is just commutative. So this is B1 plus A1, B2 plus A2, B3 plus A3, and B4 plus A4. And then that is the same as matrix B plus matrix A. And so that checks. And which is an element of, should put that, it's an element of M2 as well. Okay. So that works. Okay. I don't really think we need, was 3 a closure property? No, we don't really need the element of M2 there. We just need to know that it's the same. Okay. Okay, A4. Okay, moving on to A4. Okay, so is A plus B plus C. Okay, if I add these in a different order, am I going to get the same result? Okay, is that going to be the same as A plus, and then in parentheses, B plus C? So A plus B, we saw was, just like above here, A1 plus B1, A2 plus B2, A3 plus B3, and A4. Okay, so that's A plus B plus C. So that's C1, C2, C3, C4. Okay, that is going to equal A1 plus B1 plus C1. A2 plus B2 plus C2, A3 plus B3 plus C3, and A4 plus B4 plus C4. Okay, and what I'd like to do is I'd like to break off A, okay, and I could say that this is the same as A1, A2, A3, A4 plus B1 plus C1, B2 plus C2, B3 plus C3, and B4 plus C4, which is equal to A plus B plus C. So the associative property checks. Okay, A5, we want to know about the additive identity. Okay, so we're going to call O2, okay, matrix O2 as 0, 0, 0, 0. So the zero matrix, 2 by 2 zero matrix. Okay, and so A plus O2 is equal to A1, A2, A3, A4 plus 0, 0, 0, 0. Okay, which is equal to A1 plus 0, A3 plus 0, A2 plus 0, A4 plus 0, which is just equal to A1, A2, A3, A4, which is equal to A. So that checks. That's additive identity. Okay, A6. Okay, let negative A equal the negation of A1, A2, A3, A4. Okay, and then is A plus negative A, does that equal 0? My zero matrix. So this would be A1 plus negative A1, A2 plus negative A2, A3 plus negative A3, and A4 plus negative A4. And adding the opposite does give me zeros, which was my zero matrix. And so there is an additive inverse. Okay, A7. Okay, let 1 be an element of R, the real numbers. Okay, let 1 be an element of R. Then 1A is equal to 1 times A1, A2, A3, A4, which is equal to 1 times A1, 1 times A2. And I'm sure you can see where this is going. 1 times A3, 1 times A4, which is equal to A1, A2, A3, A4, which is equal to A. So we have a multiplicative identity, multiplicative identity. Okay. And A8, let's skip a line, A8. Okay, so A8, A9, and A10, those are kind of like, the ones where, if something's going to fail, it more than likely is going to fail in either the first two, the closure, okay, or in the last three. okay, because these are the more complicated ones. Okay. So given matrix A, A1, A2, A3, A4, and scalars Rs, which are elements of R. A is Rs times matrix A, okay, equal to R times S times matrix A. So we have Rs times A1, A2, A3, A4, okay, and that equals Rs times A1 plus, put a little parenthesis around here, Rs times A2, Rs times A3, Rs times A4, okay, which is equal to, I can regroup this, okay, using the associative property of multiplication. This is just all multiplication now inside, okay, R times S times A, because those are all of the elements inside the matrix are real numbers. So they're all real numbers being multiplied. So I can reassociate these. R times S times A1, R times S times A2, R times S times A3, and R times S times A4. Okay. And then I can pull out the R and say that this is equal to R times S times A1, S times A2, S times A3, S times A4. Okay, which is equal to R times S times A. So that checks. Okay, A9. A is R times A plus B. Is that equal to RA plus RB? So let's show that. So this is R times A1 plus B1, A1, A2 plus B2, A3 plus B3, and A4 plus B4. And I want to distribute the R. Oops, let's distribute the R to each element first. Okay, distribute the R. I won't show the distribution lines. Okay, but that's going to become R times A1 plus B1, R times A2 plus B2, R times A3 plus B3, and then R times A4 plus B4. And now we can just use regular distribution of this. Okay, normal numerical distribution, or maybe algebraic distribution, I should say. Okay, however you want to think about it. Okay, now this is RA1 plus RB1, RA2 plus RB2, RA3 plus RB3, RA4 plus RB4. Okay, which is equal to, okay, I can break this up now and just focus on the addition part. This is RA1, RA2, RA3, RA4, plus RB1, RB2, RB3, RB4, okay, which is equal to, okay, and I can factor out the R, which is equal to R, okay, which is equal to R times A1, A2, A3, A4, plus R times B1, B2, B3, B4, which is equal to RA plus RB. So that checks. Okay, and the last one, A10. Okay, R plus S, where R and S are scalars, times A. Okay, so let's go through this one. This is equal to R plus S times A1, A2, A3, A4. Okay, so this is just a scalar. R plus S is just a scalar, so I'm going to multiply that through. Okay, to each element, R plus S, R plus SA1, R plus SA2, R plus SA3, R plus SA4. Okay, that is equal to, now I can distribute RA1 plus SA1, RA2 plus SA2, RA3 plus SA3, and RA4 plus SA4. Okay, and now I can break this apart like I did before in the top in A9, okay, above it, right above it. We're going to do the same kind of procedure. We have R A1, RA2, RA3, RA4 plus SA1, SA2, SA3, SA4, which is going to be R A1, A2, A3, A4 plus S A1, A2, A3, A4. So we just kind of factored the R and S out, which is RA plus SA. And so that checks. Okay, and so we could say that, yes, M2, okay, M2 satisfies all 10 properties. Okay. M2R satisfies all 10 properties of a vector space and is itself a vector space. Okay, and then as we'll see, M2R really is what's called a subspace of MNR. Okay, it's more restrictive. It's a vector space in and of itself, in and of its own right, but it's a subspace of the vector space MNR. Okay, theorem. Okay, let V be a vector space over F. Then, okay, if it's a vector space, and then we know some things. Okay, 1, the 0 vector is unique. Okay, there's only one 0 vector and it's unique. Okay, 2, 0, okay, times a vector is equal to the 0 vector. Okay, 4, 0, an element of real number system, and for all U, which are elements of V. Okay, all vectors U. 3, Okay, k times the 0 vector is equal to the 0 vector. For all scalars, k and f. Okay, number 4, negative u is also unique. V. Number 5, for all u in V, negative u is equal to -1 times u. Okay. And number 6, if k is a scalar, and u is an element of V, such that k u, k times u is equal to the 0 vector, then we know one of two things. Okay, either from number 2, k was 0, or u was the 0 vector. So that comes to us from properties 2 and 3, or in this theorem. Okay, number 2, example 2. Is the following set S a vector space? Okay, so we're going to define S as elements of R2 such that x1, x2, we're going to define our addition property. Okay, this is an addition. This just means addition property. The plus with a circle around it just means it's we're defining what that addition property does. Okay. For this set S, we have circle plus, meaning its definition as, okay, that operation circle plus is going to be our addition operation. Okay, and if we have two vectors, x and y, okay, when we add those two vectors together, we get x1 plus y1, so that makes sense. But we then get x2 minus y2. Okay, so we're defining the addition of these vectors a little bit differently. Instead of adding the second components together, we subtract the second components. So that's a little different. Okay, and then k okay, multiplied, we're going to define this circle dot means the operation of multiplication as defined in this set. Okay, k circle dot of x1, x2. So k multiplied the scalar multiplication of x1, x2, we're going to say we only multiply the first component and we leave the second component alone. Okay, so we can kind of go through and say, well, you know, is there a property that's going to fail? Okay, for and where is that property? Okay, and we don't really have to get too far before we do see one that failed. Okay, so A1, is it closed? Okay, is it closed under R2? Okay, and we do see that when we add this together, okay, x plus y is equal to x1, x2 plus y1, y2. Okay, that is equal to x1 plus y1, x2 minus y2, and that is an element of R2, so it is closed under the addition that we're not getting a third dimension here, or a third component. We stay with two components, we end with two components, so that's good. Okay, so that one works. A2 is very similar. Okay, it's just k circle dot times x vector is equal to k circle dot times x1, x2, which is equal to kx1, x2. And is that still an element of R2? Yes, two components in that vector. And so that's still an element of R2. And so we check that. A3, we get into a little bit of trouble. Okay, so if we take x plus y, okay, we want to know, is that the same as y plus x? And we're going to see that it isn't. And so it fails right there. Okay, commutativity fails. So x plus y, we saw from above that this thing was x plus y, okay, is equal to x1, x2, circle plus, okay, y1, y2, which is equal to x1, y1 plus x2 minus y2. Okay. And then we can kind of go the opposite direction. Y circle plus x that's equal to y1, y2, circle plus x1, x2, which is equal to y1 plus x1, and then y2 minus x2. Okay, and we can see that there is going to be a sign issue. Okay, the first components work. Okay, the first components work, but the second component does not work. Okay, we know that x2 minus y2 is not the same as y2 minus x2. Those are going to give me opposite signs. And so A3 fails. Okay, so since the addition is not commutative, S is not a vector space. Okay. Okay, and that's 4.2, and I'll see you in the next section.